Good morning. My name is Alistair Thorogood, and this is the video presentation I've put together for MEC2406 Assignment 2, Dan's Flying Fish Thingo. This is the prototype flying fish I have come up with. I've modified an old fishing lure for the body with the gyroscope mounted to the front of the fish. The fish is secured to a steel rod which spins freely inside a bearing in the base. The angles used in the tests are 5 degrees, 15 degrees, and 20 degrees. These are marked on the base with a toothpick depicting the current angle of the fish. The tail is a 5mm grinding disc connected directly to the microservo. To maintain the fish's desired angle, I have utilized a PID control system. A PID control system is the addition of three contributing factors: proportional control, integral control, and derivative control. Proportional control adjusts the angle relative to the error. Integral control adds the error over time and adjusts the angle accordingly. This is used to reduce ramp time and settling time, however in my testing increased overshoot. The derivative control calculates the change in error, or how fast the error is changing, and adjusts the angle accordingly. This is used to limit overshoot. Tuning methods require adjusting the proportional control until an undamped oscillation is met. Unfortunately, my design would not allow this due to restrictions of the gyroscope, current draw, and the nature of the code. As you can see in the following three graphs, I've tried to reach undamped oscillation by increasing proportional control. 2.2 was the KP limit before the microservo tripped the inbuilt fuse. KP 0.8 was the final proportional control decided by limitations of the gyroscope. Unfortunately, any changes in integral control had negative effects on my system, and I had to leave the KI as 0. I believe this is due to the nature of my code already integrating the error. The derivative control had a major effect on the system, and I found a KD of 0.03, ideal for reducing overshoot and deviation once settled. The bottom graph shows the final PID control, and this is explained further in the report. Below is a graph of the full function of my fish, including both test 1 and test 2 from the assignment. On startup, the fish moved to an angle of 20 degrees and maintained this position for 10 seconds. I allowed 3 seconds for settling time, however this may have been too long. After 10 seconds, the fish moved to an angle of 15 degrees and held this until 30 seconds of loop time was met. The fish then moved to a final fixed angle of 5 degrees, where the base and angle of the fan were moved to introduce interference. Now let's see the fish in action. Overall, I am happy with the function and the design of the fish that I have produced. A couple of improvements I could note for next time is to make the tail more lightweight but maintain rigidity, and try and remove the inbuilt integration in the function code for better controlling. This is explained more in the report. I've enjoyed the assignment. Thank you.